Jet fuel vapor combustor. Hi everyone out there, my name is Carlos, and I am a mechanical systems strategist. This is my very first video on my channel. In this video, I am going to talk about other possibilities to improve the efficiency of modern jet engines and lower the levels of emissions in an out-of-the-box context. Let's imagine that the chief engineer, designer, and the company's investors went on vacation, leaving behind a blank check to cover the expenses related to tests and prototypes just for fun. At the same time, they saw this as an opportunity to tackle this very sensitive issue. Jet engines are a type of internal combustion engine. These engines are considered very efficient, but the reality is that piston engines, which are another type of internal combustion engine, are only around 35% efficient in terms of the output that the engine is able to extract from the fuel burned in the combustion chamber. Now, the efficiency of jet engines does not fall far from these numbers, as old and modern internal combustion engines in general face challenges regarding the efficiency of the combustion process. Although the type of internal combustion engine that uses pistons is considered obsolete in some spheres, there is more that can be done to improve the efficiency of all types of internal combustion engines, including the jet engine. The most important step towards improving the efficiency of all types of internal combustion engines or the internal combustion engine in general is to solve the challenges related to the combustion process in these types of engine. Looking at these challenges, it is noticeable that all types of internal combustion engines burn liquid fuel inside a combustion chamber. In the case of piston engines, the combustion chamber is a closed cylinder, while for the jet engine, there is a difference because the combustion chamber is basically a short tunnel that is open at the entrance and also open at the exit, called the combustor. Despite these differences in the design of the combustion chamber, all types of internal combustion engines face the same challenge: the inability to complete the combustion of all the fuel introduced into the combustion chamber at certain instances. For piston engines, this normally occurs when these engines are performing at high workload conditions, rather than during low workload conditions. However, for jet engines, they are unable to achieve complete combustion of all the fuel introduced into the combustor during both low and high workloads. Although these engines are considered efficient mainly because aircraft fitted with jet engines are able to cover large distances in a short space of time compared to automobiles while perhaps consuming less fuel. Internal combustion engines are unable to complete the combustion of all the fuel introduced into the combustion chamber mainly because combustion, as a chemical reaction, must adhere to certain principles in order to achieve the desired outcome. Modern internal combustion engines, in general, fail to meet two important requirements of this chemical reaction, which are necessary for achieving complete combustion of the fuel and air mixture introduced into the combustion chamber. The first condition is that the volume of air and fuel mixture introduced into the combustion chamber must be homogeneous. The second condition is that the same volume of air and fuel mixture introduced into the combustion chamber must be stoichiometric. Internal combustion engines struggle to meet the first condition because achieving a homogeneous mixture between liquid fuel and the gaseous oxygen in the air requires time and a thorough mixing process. This is due to the difference in states between liquid fuel and gaseous oxygen. Even the mixing of two different gases requires proper mixing and time. As a result, significant mixing must occur before the mixture can be considered truly homogeneous. Looking at this fact from another perspective, it becomes evident that all types of internal combustion engines transform liquid fuel into fuel vapor within a short period of time, as this transition occurs inside the hot environment of the combustion chamber. While this rapid transition saves time, other conditions within the combustion chamber, such as piston speed and design anomalies, hinder the mixing process. This means that not all the volume of air and fuel introduced into the combustion chamber becomes truly homogeneous. The other important requirement is that the ratio between fuel and air in the air-fuel mixture must be stoichiometric. In the case of piston engines, this condition can be easily achieved by combining a fuel injection system with a free valve mechanism and a supercharger. However, the use of superchargers is often seen as wasteful in terms of the engine's energy, and the importance of free valves may be overlooked in piston engines. While this topic deserves a more in-depth discussion, it is beyond the scope of this video, which focuses on jet engines. In the case of jet engines, achieving stoichiometric air and fuel mixtures becomes even more challenging. Some jet engines only have a diffuser, in certain cases, to slow down the speed of the air entering the combustor, but there is no other mechanism regulating the volume of air that enters the combustor. Although the fuel nozzle can control the amount of fuel injected into the combustor, achieving the ideal air-fuel mixture remains difficult. Returning to the issue of achieving a homogeneous mixture, it's important to note that the transition from liquid fuel to fuel vapor occurs inside the combustion chamber of both piston engines and jet engines. However, focusing on piston engines, due to their working principle, there is insufficient time to create a homogeneous air-fuel mixture. This transition from liquid fuel to fuel vapor occurs only after the fuel and air are introduced into the combustion chamber, where the piston is moving rapidly up and down. It is only after this transition that the mixing process towards a homogeneous mixture can begin. However, due to the limited space inside the cylinder as the piston moves towards top dead center during the compression stroke, the chances of achieving a well-mixed fuel-air mixture decrease. This lack of sufficient mixing time means that some of the fuel vapor does not mix well with the air during the inlet stroke process inside the cylinder. During the compression stroke, as the piston compresses the contents of the cylinder, only a portion of the air and fuel mixture mixes well, while the rest does not. As a result, when combustion occurs inside the cylinder, only part of the mixture undergoes complete combustion, leading to high levels of CO2 emissions, carbon monoxide, and increased fuel consumption. Shifting the focus to the combustion process in jet engines, we encounter a similar challenge. In the case of jet engines, the air and fuel are injected into the combustor, and the mixing process takes place inside. This mixing process inside the combustor is the primary cause of flame oscillation and temperature instability in gas turbines and jet engines. The design and working principle of modern combustors are unable to sustain 100% homogeneous air-fuel mixtures or stoichiometric mixtures. Considering the design of the annular combustor, which is considered the most efficient type, and the fact that liquid fuel needs to be transformed into fuel vapor before it can mix well with the air inside the combustor, several challenges arise. The combustion process of the air and fuel mixture inside the combustor occurs a short distance before the mixing area, without any physical barrier separating the two regions inside the combustor. Additionally, the speed of the air entering the combustor towards the exit is relatively high, and there is only a curtain of air from the perforated area around the combustor to prevent the rushing air from entering the combustion zone. Consequently, a significant portion of the air cruising through the tunnel-like corridor inside the combustor will pass through the air curtain without being mixed with any fuel. Only the recirculating fuel in the mixing area of the combustor will reach a homogeneous state. These circumstances are unfavorable for achieving a homogeneous air-fuel mixture, as proper steering and sufficient time are required for this process. While some fuel will mix well with the air, not all of it will, resulting in a combustion process that predominantly consists of rich air-fuel mixtures. This leads to the release of high levels of CO2, carbon monoxide, increased heat generation, and higher fuel consumption. Considering the challenges faced in the combustion process of both piston engines and jet engines, it becomes evident that a new combustion strategy is necessary. One simple and effective solution is to change the route of the combustion process in internal combustion engines, favoring a longer route. This can be achieved by introducing a small-scale fuel processing plant into the combustion mechanism apparatus. This processing plant would transform the liquid fuel into fuel vapor before it is mixed with the air. This vaporization process would occur prior to the introduction of the air-fuel mixture into the combustion chamber or combustor. In other words, the air and fuel would be thoroughly mixed until the entropy is at its lowest point, resembling an organized chaos, before being introduced into the combustion chamber or combustor. This approach would allow for the highest level of entropy to be obtained after combustion, resulting in increased energy extraction from the air-fuel mixture and reduced emissions released into the atmosphere. While some may perceive this as a longer route, it is the only way to adhere to the principles of combustion as a chemical reaction, while simultaneously reducing fuel consumption and emissions. When considering the configuration of piston engines and comparing them to jet engines, it is relatively easier to address the combustion challenge in jet engines. This is because the combustion mechanism apparatus in jet engines is simpler and provides ample space to accommodate a small processing plant for transforming liquid fuel into fuel vapor. By doing so, a proper homogeneous air-fuel mixture can be created before reaching the combustor. Additionally, there is an opportunity to meet the requirement of stoichiometric air-fuel mixtures by incorporating a mechanism that regulates the volume of air mixed with the fuel within the fuel processing plant. To implement this modification in jet engines, I have chosen the turbofan engine, known for its efficiency, although improvements are still necessary to truly classify it as efficient. I propose placing the fuel processing apparatus above the low-pressure compressor in the bypass area. This area experiences relatively lower temperatures, ensuring that the preparation of the air and fuel mixture is not adversely affected by the heat generated in the engine's core. The fuel processing apparatus consists of three primary components: a vaporizer, a mixer, and a reservoir called the flask. Each component will be housed in a separate compartment within a metallic cylinder designed to prevent combustion and the spread of fire. This fire-resistant tunnel is divided into three compartments by metallic walls, preventing the spread of fire between compartments. Each compartment has a pipe connected to a larger pipe called the fire discharge pipe, which extends from the fire-resistant tunnel above the low compressor to the rear of the jet engine. This pipe passes through the area where hot gases from the combustor are discharged. Heat seals controlled by sensors are installed on the pipe to keep them closed, preventing the heat from the rear of the engine from entering the compartments. However, the sensors and the engine's electronic control unit can command the seals to open in case of a fire in any compartment, allowing the flames to be expelled at the rear of the engine. In addition to the fire-resistant tunnel, other components will be located above it, including the center fuel tank, a special air separation unit, a rich oxygen air tank, a low-compression air tank, and 2 superchargers. These components supply the mixer with rich oxygen air and fuel to the vaporizer. A vacuum pump is also installed to remove residual gases from the 3 compartments of the fire-resistant tunnel before starting the engine. Now, let's delve into the working principle of this small-scale fuel processing plant and explain the steps involved in processing the air and fuel until a final homogeneous and stoichiometric air-fuel mixture is delivered to the combustor. This explanation assumes that the start sequence of a jet engine equipped with this type of fuel processing plant has been initiated. The working principle of the fuel processing plant can be explained as follows. 1. Initiation of the start sequence. From the cockpit, the auxiliary power unit is engaged to provide high-pressure air. This air is directed to the accessory gearbox, which houses various pumps and an air starter unit consisting of a turbine connected to a shaft. As the high-pressure air flows through the ducts, the turbine and its shaft start to rotate, causing the N2 shaft to also rotate slowly. Ignitors inside the combustor are activated. As the N2 shaft speed increases, the N1 shaft begins to rotate, drawing air from the front fan section of the engine and building up air pressure. 2. Fuel processing outside the combustor. Unlike a regular jet engine, where fuel is introduced into the combustor for mixing with air inside, in this case, the air and fuel mixing process occurs outside the combustor in the small-scale fuel processing plant. This process is controlled by an electronic control unit and is powered by the aircraft's batteries. 3. Drainage of residual fuel. The start sequence initiates the activation of drain valves located at the bottom section of each component inside the fire-resistant tunnel. These valves simultaneously drain the liquid fuel residuals from the previous flight into a fuel drain manifold connected to a fuel return pipe. The collected fuel is channeled into a reservoir for treatment and reuse in the center fuel tank. 4. Vacuum pumping to sterilize components. After the drainage process, a vacuum pump located above the fire-resistant tunnel is activated. The pump has 3 pipes connected to the vaporizer, mixer, and flask. It suctions the fuel fumes from the components, reducing the pressure close to zero, sterilizing the components, and eliminating any contamination from previous fuel or fuel vapor. This step aims to minimize the conditions favorable for combustion inside the components. Once the process is complete, the vacuum pump is deactivated, and switch valves disconnected from the 3 components. 5. Fuel processing initiation. With the vaporizer, mixer, and flask ready for fuel processing, the fuel pump in the center fuel tank pumps liquid fuel through a pipe into the vaporizer. This pipe includes a block valve and a heat sensor near the entrance of the vaporizer. The sensor detects temperature increases and commands the block valve to shut off the fuel pipe in case of a fire inside the vaporizer, preventing the spread to the center fuel tank. 6. Vaporizer operation. Inside the vaporizer, the fuel is heated to a specific temperature, well below its self-ignition temperature, to prevent the risk of fire, even in the absence of oxygen. The vaporized fuel accumulates in a heat-proof tank within the vaporizer, known as the fuel accumulation tank. This tank is equipped with a poppet valve at the bottom, which opens at a specific pressure and closes below that pressure. The fuel vapor is then channeled through a pipe to the mixer in the next compartment, passing through a metallic wall that separates the 2 compartments. This is the initial stage of the fuel processing plant, where the liquid fuel is transformed into fuel vapor and prepared for further mixing with air to achieve a homogeneous and stoichiometric air-fuel mixture. The subsequent steps in the fuel processing and delivery of the mixture to the combustor can be explained in subsequent section. Continuing from the previous section, the fuel processing plant operates as follows. 1. Supercharger and fuel vapor delivery. In the next compartment, the pipe from the vaporizer is connected to a supercharger. This supercharger draws the correct volume of fuel vapor from the fuel accumulation tank in the vaporizer. The fuel vapor passes through a common rail pipe to stabilize the pressure, and a free inlet valve at the entrance of the mixer opens to allow the fuel vapor to enter. Once the fuel vapor is introduced into the mixer by an injector, the free inlet valve closes to prevent the mixture from escaping. 2. Special air separation unit and air supply. Above the fire-resistant tunnel, there is a special air separation unit that supplies rich oxygen air to a small air tank. Since harvesting rich oxygen air can take time, cool air from the atmosphere is also drawn through a pipe connected to a supercharger and stored in a low-compression air tank. A block valve on the pipe allows the supply of air from this source to be stopped when not required. The supercharger, along with the rich oxygen air and cool air, delivers the correct volume of air into the mixer through a pipe with a free valve at the entrance. Once the correct volume of air is delivered, the free valve closes since the combination of the correct volumes of air and fuel creates a 100% stoichiometric mixture. 3. Homogeneous mixing. A shaft with flaps, driven by a small electric motor at the bottom of the mixer, rotates to steer the fuel vapor and air inside the mixer, ensuring a 100% homogeneous mixture. 4. Pressure release. On the top section of the mixer, a pressure release pipe and pressure sensor are installed. If the pressure inside the mixer exceeds the recommended level, the pressure sensor commands the switch valve on the release pipe to open. This allows the excess air and fuel mixture to be channeled into the fire discharge pipe and subsequently expelled at the back of the engine core. 5. Connection to the flask. A pipe links the mixer to the flask, passing through the metal wall that separates the two compartments. On the flask side of the barrier, a supercharger is fitted on the pipe, along with a heat sensor and a switch valve. The heat sensor detects a fire in the mixer and commands the switch valve to close, preventing the spread of fire to the flask. The supercharger draws the mixture produced in the mixer and delivers it to the flask, where it is kept as a ready, stoichiometric, and homogeneous air-fuel mixture. 6. Recirculation and pressure control. Inside the flask, the ready air-fuel mixture undergoes a constant recirculating process to maintain its properties. A slow turbine inside the flask ensures the recirculation, to maintain a constant pressure as the volume of the mixture decreases. A pressure control piston driven by an electric motor is installed in the flask. The ECU commands the activation and deactivation of this mechanism. 7. Delivery to the combustor. The ready air-fuel mixture is then delivered directly to the combustor, where it meets the hot igniters and undergoes the combustion process. Once the N2 shaft speed reaches a certain level, the shafts from the air starter unit and the high-pressure air source can be disconnected. The flame becomes self-sustainable, and the combustion process proceeds. The preparation process of the air-fuel mixture in the fuel processing plant takes some time, but the resulting system provides excellent fuel efficiency and significantly reduces emissions compared to modern jet engines. Implementing this system on commercial airliners and even fighter jets can offer a simple, cost-effective, and environmentally friendly solution to present-day environmental challenges. It can serve as an interim solution until electric planes and other technologies become more feasible. This system represents a way for oil companies and engineers to contribute to the improvement of modern combustion engines, from jet engines to piston engines, in terms of fuel efficiency and pollution reduction. Combustor. The design of the fuel vapor combustor will differ from a regular annular combustor. The entrance from the side of the high-pressure compressor will be closed, and the ready air and fuel mixture, which is 100% homogeneous and 100% stoichiometric, will be delivered directly from a special fuel nozzle designed for this purpose into the combustor. The combustor will not have a mixing area or holes drilled on it. It will be a simple combustor consisting of a combustion chamber and fuel igniters. In this design, the air will flow directly from the high-pressure compressor and pass around the combustor. This serves to cool the temperatures inside the combustion chamber. The air will then continue on towards the high-pressure turbine, where it will combine with the hot gases produced in the combustor. This configuration helps maintain the integrity of the homogeneous air and fuel mixture as it progresses through the engine.